Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So today's guest is Professor Duraisamy, who is a professor at the University of Michigan and is also the director of the Michigan Institute for Computational Discovery and Engineering. And he has become actually one of the key voices in this area of AI for science, coming from the fluid dynamics background. In fact, actually, we discussed that many of the people moving and being pioneers in AI for science, which covers, of course, science in general, actually coming from a fluid dynamics background. And he is probably, to some, best known for his work actually in turbulence modeling, in the sense of the seminal paper that he did, Turbulence Modeling in the Age of Data, that back in 2019, although as we discussed, he actually started that work 2012, 2014, which was well before the current hype and rise of machine learning and AI. And that paper and that work really, I would say, motivated the whole community to really look at machine learning. And he's progressed from that point to actually broaden out, not only into more general fluid dynamics, but also covering, the sciences and really focusing in the role of machine learning and AI. In fact, one of the specific areas that he has really tried to push in recent years and bring the community together is around foundational models for science. Certainly a hot topic and something of potentially huge significance. So in this episode, we mainly focus on these debates around AI for science, and we do limit ourselves a little bit into the fluid dynamics and computational fluid dynamics domain, but really trying to get a sense of where this field is going and hear some of his thoughts, starting in the turbulence modeling side. So where does he see the current progress when it comes to using machine learning in that side? And he's careful to remind everybody that he's not trying to say that this replaces the need for humans. It's just an additional tool that they can use in the development of these methods. And then we broaden the discussion a little bit to go into more surrogate modeling and his thoughts around, PINs, physics-informed neural nets, how he sees their potential to replace, or does he see their potential to replace PDs, solvers? And then we really get into a reasonably detailed discussion on foundational models, what he believes foundational models are, his thoughts on maybe even how large language models using transformer architectures could still be used in many parts of scientific discovery, but using simulation tools as agents within that. I thought that was a really interesting part of the discussion we had. I also asked him about the role of academia and industry and startups in this space. And we have a discussion around also some of his advice for students and aspiring academics, and some of his opinions on his enjoyment of being in academia and the career path that he's taken. As with, I say this in almost every single episode, even though this, we spoke for more than an hour, there were many topics we didn't really get to cover. And that's why I put some links in the chat. Certainly if you're watching this on YouTube, if you're listening to this on Spotify, Apple, maybe you can go to the YouTube channel to see some of those links where some of the summer schools that he's organized and symposia, which had some really fantastic speakers. And also, I think they have some of the slides and talks that he gave where he goes into even more detail into some of the specifics that perhaps we weren't ever able to get into in this episode. So, this is along the theme of, as I mentioned, the past episode we did, and there's a few more coming, that really focuses on this AI for science, and he is really a key voice in this that I hope you'll learn a lot from. So please sit back and enjoy this episode with Professor Duraisamy.
the MICDE, or the Michigan Institute for Computational Discovery and Engineering. So it's an institute across the entire campus. There are more than 180 faculty members looking at all kinds of disciplines, from computational medicine to biology to astrophysics to climate modeling. But of course, as a researcher, my applications tend to be somewhat close to fluids, but not in the sense of 7 or 8 years ago. So my work has maybe moved closer to computational science and AI rather than fluid specific. But of course, many of my applications tend to be close to fluids, but not exclusively.
Okay, yeah. I mean, it's always nice, isn't it, to expand a little bit. I guess there's a trade-off, isn't there? Like, there's a lot of transferable knowledge from, I guess, fluid dynamics outside, which is useful to bring. Do you think that's important, particularly in the age of AI, where methods are coming from different disciplines?
Absolutely. In fact, since we are on this topic of institute directors, a few months ago, I kind of had a consortium of institute directors across various universities. There was Petros Koumoutsakos at Harvard, Kellen Wilcox at Texas, Gianluca Iacarino at Stanford, Yusuf Marzouk at MIT. And what is common to all of these people? Fluids applications. It's kind of weird, right? The institutes are very broad in scope, but I think because of the scale of the problem and certain peculiarities about fluid dynamics, I think some of the knowledge and methods that we develop here tend to be asking questions that are very hard. And so I think assimilating other information or taking these to other methods, I think it's a bit of a bridge, but of course I could be biased.
It sounds like a good career advice for people. If you want to become the director of a top institute, go down the fluid dynamics route, because statistically,
or the other way to think about it is, if you never want to solve the problem that you want to solve, you want to pick fluids and turbulence in particular, but you'll gain so many different skills in that frustrating process of not being able to solve anything. I'm being tongue-in-cheek here, but seriously, I do think there is something here, right? Because if you look at the development of computational fluid dynamics, it has a very strong connection to numerical methods in general, right? And in many other disciplines, you can see like a diffusion of these ideas. But yes, there is certainly some of the problems are so hard, and there is this quote. I don't know who said it. It said, "Turbulence is the graveyard of all ideas that are successful in other fields." But you can also flip that, and you can say many of the methods that we use to probe turbulence and model it, can have applications in many other disciplines, because this is, in a sense, a hard and intractable problem. But end of the day, I'm still an engineer, right? So we still can get very useful things out of it.
Yeah. I maybe want to start a little bit on, and it'd be good to, please correct me if I'm wrong, but I think one of the areas that really brought you to the national or international stage was the pioneering work, the turbulence modeling paper that you did, looking at data-driven turbulence modeling. At least from my side, I found those papers and those review papers incredibly useful, and I know many other colleagues. It sort of brought it to the attention to the point, I would say, arguably now, so many people I know, at least in the fluids domain, have PhD students, have projects, and many of them are citing that sort of as an original piece of work that sort of kick-started a lot of this off. Turbulence modeling in the age of data. Was that also your sort of first move into machine learning and sort of more data science from your prior background, maybe more as a pure quote-unquote turbulence modeling or engineer?
Yeah, there is. First of all, that paper you referred to we wrote it in 2018. That was already 6 years into the work that I've been doing in the field. But you're right, that is the first entry for me into data science, machine learning type of areas. And I was never really a turbulence modeler as you or your advisor were, but it was certainly a good chunk of my thinking back in 15 years ago or so. And the entry into the field was a bit interesting. So I was working on this idea called structure-based turbulence modeling. It's very advanced. So think of writing equations for a three-dimensional tensor. So 27 equations. Of course, there are symmetries and things. You can eliminate a few. And there, even though we were going more and more fundamental into the theory, by the time you were developing a true turbulence model, there are just so many uncertainties, so many functions that we had to make up, so many coefficients we had to fit. So we said, yeah, this is probably a task that data science can address. And of course, at that time, big data was everywhere. So this is the world of Walmart saying big data is going to be the next big thing, kind of thing. So yeah, that's how I entered the field. You're right in that sense. And I started this in this 2012, 2013 timeframe. And I think for a few years, there was literally nobody, at least in turbulence and CFD, doing that. At least, for these kind of problems. And then, the field kind of took off around 2016, 2017.
Yeah, that's kind of incredible in a way. Now, when you look back, it's hard to split the now to then, because now machine learning AI is literally everywhere. You can't even watch the television, listen to anything without it being on. Where probably in 2012, 2013, was it even a struggle to get funding? Were the funding agencies not even fully appreciating it? Or was it, as you say, more under a different banner, this big data banner?
No, I must count myself lucky, because the very first proposal I wrote when I came to the University of Michigan, I think it was called Turbulence Modeling. I think it was something to do with big data and turbulence modeling in the title. And it got funded. It was one of, I think they had, I submitted to NASA. I think they had about 90 proposals, and they funded 4, and it happened to be one of them. So I was lucky in the sense that when I started, even before my ideas were fully formed, I just shot out a proposal and it got funded. And I must say, it has not been a struggle at any point to get funding, because maybe I got the timing right or whatever, or I asked the right questions, I don't know. But being ahead of the curve in terms of, what needs to be done or what needs to be looked at, I think helps. But that doesn't mean the problem is anywhere close to being solved, as I mentioned earlier. But it has been, that was my entry point. And it's been good to be close to the center of the field and see what people have been doing.
So maybe for people who are not as familiar, how would you describe the state as it is now? I mean, essentially, I think still it's quite a ferocious debate, depending on how close people are to the research, perhaps. Some on one side of the coin being almost anti-machine learning, anti this sense that it's just all hype and why are we even doing this, to the other side that really do see it as being, the next generation of methods. I know we'll maybe expand this to a broader debate around scientific foundational models, but on the turbulence modeling side, how would you summarize how it is today?
Yeah, so, I've been saying this almost, first of all, I think you're right. There has been ferocious debate right from the beginning. And I don't know which side is louder right now. But I think if you want me to summarize the state of the field, I want to separate a few things here, right? One, early on especially, and maybe even recently, when somebody publishes a paper saying, hey, here is a method, right? So from the viewpoint of the person who publishes it, the viewpoint of the turbulence modeler, they're looking for a model. They're not looking for a method, right? So there is that disconnect, which I think can be bridged better by being very clear about what the objective is, right? But beyond that, I've been saying this all the way from 2013 now, maybe as a way to, hedge. I don't know why I started presenting my work this way. So I would go through this hour-long talk on data-driven turbulence modeling. And then at the end, I would say, I have not presented to you a new approach to turbulence modeling. I'm providing a new tool that you can use, right? And from that perspective, what have we been doing as a community from 1960, right? We have some ideas, we put together a model, and then we leave some coefficients to be calibrated. And in the way, we make up some functions, right, along the way. And then using some very few data points like the log layer and jets and things like that, we calibrate coefficients or constants. So at least my view has always been, do not abandon that by any means, but use these new tools, right, which can potentially help you ingest more information and maybe do things in a better way. But that doesn't mean, again, I do not want the focus to be on the machine learning. In fact, I organized a very successful conference in Ann Arbor about 2017, and I was on a warpath. It was on data-driven turbulence modeling. I said we should never use machine learning in the abstract or in the title, because that is one piece, right? The modeling is the most important piece. And then the data is another piece, right? So the machine learning is a little tool in this process. And even without using it, there are many ways to massage the data, right, to get you the information you need. So it is a tool. And I do not think a machine learning first or an AI first approach, at least in turbulence modeling. And we can talk about other fields where purely data-driven machine learning type of or AI approaches can take you almost all the way. But here it is a tool in the modeler's toolkit. And to use it judiciously, as you have been using it in the past, right, without overfitting, etc. I think that's the way forward. It has always been the way forward, in my opinion. Even though I would publish a paper, I did not claim to say, I have solved this problem. I say, here is a method you can use with your own judicious interpretation of what needs to be done with this tool.
Yeah, I guess it's always like with anything, there's always an overreaction to things sometimes where people, but I guess the turbulence modeling community in general has a large sort of quite conservative nature, I would argue as well, which probably makes it even harder for newer methods to perhaps come in to the phrase, because people are used to doing it a certain way. And I guess this would also, I'm not as familiar, but I would assume transition models as well are equally, maybe slightly changing angle a little bit. I think one of the areas you also work on is some of the hypersonics work, and I believe transition modeling is one of the most complicated parts of that. Have you seen equally that, for all these models with tons of coefficients and models that machine learning can play a part also in transition modeling, that it's not just about turbulence modeling per se?
Yeah, there's certainly quite a bit of work. And I've always said this, that I think even though neither problem has been solved to an extent, that, we would be happy with the methods, I've always maintained that transition modeling may be more amenable to these data-driven disciplines, because at least there is a hope that you can cover many possible regimes using high-fidelity data and experiments, because the Reynolds numbers tend to be smaller by definition, right, than the other way. But of course, in some senses, the quality of measurements has to be better. But I think especially when, the field has become more model consistent, I can tell you more what that is. The ability to work with integral data like skin friction or heat transfer, or wall heat flux can still drive these models. So I think in a sense, I would say about 20% of the work may be moving towards transition these days. That was not the case earlier. And one of our first applications in this field was bypass transition modeling, or at least methods for bypass transition modeling, to be more precise. So yes, there is a lot happening in the field, and the fact that it is possible to run a DNS or at least close to the condition that we want, and that being a rich source of high quality data, I think is something that is very useful.
So the turbulence modeling on one side, so you could argue you're still, as you said, maintaining, you're still using a traditional solver, whether it's commercial solver, open source government, and you're plugging in your tuning coefficients. One of the points that you brought up, and there seems to be strong interest, is replacing all of it via a surrogate model. What's your view on that? Is this, let's say if we take, just for now, like let's say an external aerodynamic example, like an aircraft, do you see that a turbulence modeling machine learning fix is the way to ultimately get more accuracy and speed and all the merits that people discuss? Or do you see that actually a surrogate model is the sort of better route and better angle given the advances in machine learning?
Yeah, I think it certainly depends on the application, how that computational result is going to be processed. If you're doing design exploration, I do feel that a surrogate model for quantities of interest can take you, can give you a lot of benefit, right? But if you are going to be probing some details of the flow physics, and you want it to be somewhat general, I do not think a surrogate model can get it done unless you parameterize the problem, and there are a few parameters and you hit parameter space properly, and then you can crunch through some large data. You can't quite do it. The reason tends to be the following, right? Like, whenever we think of a surrogate model, we think of a system, right? And you have a lot of data on that system, and you want to be developing some representation of that system. But take the classical CFD turbulence modeling approach, where you can, at least in theory, run a problem for which you have seen no data for, right? A different system from the systems or subsystems where you trained your model, right? So that's the whole discovery process, where, let's say you want to design a hypersonic aircraft. Maybe I have data for an inlet. I have data from some shock boundary layer interaction. I have some heat transfer data. The advantage of going through the classical CFD/PD route is you can, in principle, extract information from these different subcomponents. And if you do that properly, you can take that to this unseen problem, right? Whereas if you go with a surrogate, you do not have that flexibility. You have to have data from that system or a parameterized version of that system. And if it is a discovery task, then you cannot get off the ground, right? So that's why I think, as I said earlier, machine learning is a tool in the modeler's toolkit. All of these are tools in the designer's toolkit. So they help you address different parts of the design or discovery or analysis process. So yeah, both have a room. And in certain circumstances, it makes a lot of sense to go with a surrogate model for quantities of interest. And in many cases, it makes no sense to do that, right? And go with this other approach. So yes, both need to be viewed as sources of information to address different parts of the spectrum.
But what about physics-informed approaches, physics-driven approaches like pins that, depending on the paper you read and the person you speak to, have a much bolder claim of ultimately being able to solve the PDEs and therefore potentially move away or combine those two together in the sense of being able to not be relying just on the data that you've trained it on. What's your opinion on those methods?
Yeah, so I have worked on pins almost from the early days of pins. Obviously, I looked at George Karidakis' papers and other things, and from probably the very first week, it was put on archive, or maybe even before that, because I think one of the students had given a talk. I've been trying it, right? So I think if your problem is simple, right, and you do not have a code, I think it's a good idea, right, in the forward sense, in terms of solving a PDE. But where it, runs into tough ground is we are pretty damn good at solving PDEs. Over the past century, we have so many reliable methods. And putting the PDE in the loss function, there are a few things that are not appealing, right? First, it's in the loss function. So by definition, you're not solving it exactly. You're, reducing the residue to some level. And that may be okay as a surrogate model in some applications. But even more so, right, if you think about all of the things we have learned in our numerical analysis classes and in our compressible flows, is the discreteness of the problem matters, right? Your weak form matters. You have Riemann solvers. A continuous form is not the same as a discrete form. So you kind of lose that, at least in the classic formulation of the pins. And there are some approaches that try to approach it from a different way, like Petros Koumoutsakos at Harvard. He has a method called ODIL that tries to keep the discrete form. But even if you ignore whatever I said so far, purely in terms of speed, I have a hard time believing that for complex PDEs, these methods can beat conventional ways of solving PDEs, just because I think the baseline is really good. So this is how, maybe we'll get into this later, when I talk about what are all the successful problems in AI for science, and I list a few things, and PDEs will almost never be there. And that's partly because the baseline is very good, right? We are very good at solving PDEs. All of that said, when you go the other way, inverse problems, then I find a good application for pins. I still can't say it's the best in class. It may or may not beat, it probably will not be the best approach to do inverse problems using classical methods, but it may be competitive, and it does not have to compete against 100 years of accumulated wealth of knowledge. So again, to summarize it, in certain circumstances, as a surrogate, it could help. And there are also hybrid versions, right? You can inject some physics, you can inject some data, and it has that flexibility without all of this machinery that we need. And your entire code could be like 60 lines in PyTorch instead of 60,000 lines. And the inverse problem solutions, so it has a place there.
Yeah, I must confess, I always find it's a tricky one, because there's so, like I guess in the early days of any field, there's so many counterclaims and claims that it is sometimes hard to have a truly independent view in it. I suppose you have to ultimately, like you do, you have to get into the code, you have to look at it to really understand it. But there was one comment, maybe this is a bit of a segue into the AI for science, when I was speaking to one of the previous guests, that scale has become the main thing that actually what has solved many of the large language problem issues is just the sheer amount of data, and to the point that is the focus, not on the accuracy of the individual or the beauty of the algorithm. So with that in mind, and this discussion of data versus physics driven, is the real problem for fluid dynamics and more generally AI for science just the data? And if we solve that, actually we will come a long way, and we're just trying to solve a problem with so little data that's really the issue?
So obviously, like, having more data helps. It can only help if we use it the right way. But if you want to like solve hard science problems, I don't think any amount of data would be enough, or the amount of data that would be required is so large that is not the main problem, because we just cannot reach there, right? Again, unless your problem is so well defined, like AlphaFold, or going from amino acid sequences to protein structure. So there, the problem is so well posed, I shouldn't say well posed, but conducive to this kind of approach, right? But because you asked a more general question, I do not think that data is the biggest bottleneck, because you will not have enough to like do that. So inductive biases or being able to bring in physics, intuition, and I need to be very clear, the right or the most appropriate level of physics, not anything you think, not some nth invariant of something just because it feels appealing to us. People talk about symmetries, invariances, beautiful ideas, nothing wrong with that. But is that the most important thing for you to get the answer you desire? Or is that one other way of constraining the model to do what you think it should be doing with that information? Or should you be just doing something else to get it to where you want to go? So, again, if the question is well posed and you have a means of acquiring the data, then I would say data is the biggest thing, right? So again, going back to AlphaFold, I think they only had 170,000 proteins or something like that. That's not a lot. The combinatorial space is immense, right? And they were able to really solve the problem and advance the field. But if you take something like turbulence modeling, in general, data is not the answer. But if you have a system or a class of systems you care about, and you have your data-driven modeling tools, and you have a connection to some experimental or numerical simulation approaches that can get you the data you want, then, yeah, I would say data is the most important piece. So it depends on how your problem and what you want to do with that.
So maybe this is a good then segue to this discussion around foundational models, because I think this, at least with some of the people I speak to, is the most contested or argued point within science, that just as large language models seem to be able to do so much without being explicitly taught the grammar of a language or explicitly done something, then logically, and people even confuse the terms and say, well, can we not build a foundational model for science or a foundational model for fluid dynamics? Where do you put recently on, I believe, a very successful symposium looking at this question of foundational models for science. So maybe you could introduce a little bit the challenge and some of the ways that you think we can address it.
Yeah, this is a favorite topic of mine also, because in our institute, just earlier this year, we started a new center on scientific foundation models. So there are foundation models for science, and then there are foundation models for particular domains within science. So I want to make the distinction, and we can cover both. But I think to answer your question, so by definition, right, these foundation models tend to do general things in a very broad domain, whereas the classical AI techniques in science, they tend to have a narrow application, and they tend to do something specific, right? So some people say broad and shallow and narrow and deep, but I don't want to go that route. But I think the discussion around large language models has been incredibly fascinating, right? So because that was maybe for natural language, it has really been surprising even to, I think, OpenAI. I do not think they expected 3.5 to make that much of a splash, because they pretty much had whatever we saw in November 2022. They had it a year ago. They just put an API, right? But I think the buzz can be explained in many different ways. So one is the ability of these large language models to bring together different concepts and compose them, right? That, I think, is what I think caught people off track. There's a beautiful paper from Princeton, from Sanjeev Arora's group, where he defines topics and skills, right? A topic could be sewing or mending or whatever, right? And a skill could be a metaphor, could be a skill. And then he passes these topics, and then he, in his prompt, he asks the prompt in such a way that many of these skills and topics have to be covered and composed, and then you get answers. And what he found was the larger the model, the more composition was happening, right, between these topics. And he made a very clear argument that the combinatorial space of topics and skills is so large that it is impossible for this to have seen all of this in the data, right? So the ability of these models to compose and combine these different topics to a degree. If you go more than 7 or 8 compositions, it breaks down. And the small model would break down at 3. So there is already something like intelligence there. And so to me, even if these large language models do not get much better, I think they can still be extremely useful, right? And I have a lot of thoughts on it, but I want you to ask me something more specific so that we can hit what you want to hit and not what I want to wrap.
No. This is good. So maybe one question is, do the architectures and the methods that are used for current foundational models for things like ChatGPT or Llama or etc., can they be used largely as is or with minor modifications for applications in science, or do we need completely different architectures to deal with? So at a high level, is it just a matter of using the same thing and just plugging it into different data sources, or do we need fundamentally different approaches than the sort of transformer style that has been used to date?
I think the answer is both, right? Let's talk about the first thing. Let's say you want to have a scientific version of GPT-4, right? So as you said, plugging into different data sources is certainly a start, and I think that would certainly be something that would already be very beneficial. So, for instance, I was working on a fairly complicated mathematical derivation a few months ago, and I would have pinged GPT-4 about 50 times, no less than 50 times, during the process about, some statistical expectations and some expressions that I was struggling to derive. Maybe 49 out of those 50 times it was wrong, but 50 out of those 50 times it was useful, because I was prompting it, and it was always telling me, pushing me in directions that, as a reasonably sophisticated expert, I could use that information and know that, okay, it is doing this arithmetic or this math wrong, but it's thinking in the right direction, right? So, so that's why I feel there is a place for these. And if you look at what GPT-4 and some of these other models have been trained on, we'll never know what GPT-4 is trained on really. But, something like Google's PaLM, they've released at least some statistics on what they trained on. Science tends to be less than 5% or maybe 3% of the entire data corpus. sports was probably bigger than science. Entertainment was probably 20 times bigger. I don't know. But so just changing that balance is going to be enormously useful. And our colleagues at Oregon National Lab have actually started that process of curated scientific data, from journal papers, and guiding the process. So I think that even if the base is just a large language model with some multimodal capabilities, I think that is still going to be very useful in many different tasks. And there's also this confusion or maybe misguided emphasis on these things being able to solve you problems. But I think the best use of these models, in my opinion, at least for the next 15 years, nobody can predict the future, but at least the next decade, is to use these as assistants, right? For things that you want to be doing, and for this to be doing the low end of the scientific process, right? You were still, looking at the details and you're guiding it. But yeah, to answer your question more directly, I feel even a GPT-4 like base, but architecture, but with the right data can take us a long way. But I also want to talk a little bit about, even within this architecture, there is a lot we can do to improve the output, right? For instance, these things are trained to complete the next token, right? In at least supervised, unsupervised pre-training, they just complete the next word. And it's not really, as some people say, thinking before speaking. But if even that part can be iterative, I think you can still get a huge performance gain. Okay. And being able to provide additional context or being able to connect it to agents that can go look for other things. Even this architecture, even if the architecture doesn't get better and even if the language part of the model doesn't get better, if it's done right, I think it can be massively beneficial for science, broadly speaking.
So are you referring a little bit more to the idea of during the conceptual phase, so not simulations now, but just more scientific discovery, like developing a hypothesis or analyzing flow fields, or you're saying that you could be using these transformer style models to help in that side, not just the replace physics-based simulations by a machine learning model. That's kind of what you're...
Yeah. So I only answered the first part of your previous question, right? I said, if we just stick with LLMs and transformers, even if we do that, right, with some tinkering with the way it's trained, like I said, not just complete the next word, but maybe it wants to iterate. And that's not too hard to do. So I think that will automatically help. But then, and it can help data processing, it can help you, code up, it can help you in so many ways as scientific assistant. But for other more regular science tasks that we do, of course, transformer architectures on their own won't cut it. We need newer architectures, and I wouldn't even say newer. Most of these things have existed in some form for a while. We just, as you said earlier, we are scaling it up, and we are, I would say, we can unhobble it as Ian Foster from Oregon says it. But yes, different architectures, but not necessarily completely radical. That doesn't exist so far.
So with that, like maybe diving into perhaps some examples then, because I've always been having this sort of theoretical debate with some colleagues. So if you wanted, what do you see as the definition of foundational model? Is it really realistic if we just look at CFD? That instead of using a code by company X, that you put the settings in, that it could be economically viable, that there could be a model trained on enough incompressible, compressible, low speed, high speed, you know, all different flow regimes that you could essentially then give it a geometry and it has seen somewhere enough to be able to give you an answer? Or do you see that it is more likely a quote unquote foundational model that is for a particular flow regime or a particular use case?
Answer could be both, but if you'd asked me maybe 6 months ago, I would have said the first thing is fiction, but my thinking has evolved on this. And there's also been some work trying to train these models on different kinds of domains and introducing boundary conditions by masking and things like that. So I think it is possible, right? So think about it is, but your question was to get an answer. We will get an answer. And I don't think that answer will be terrible.
Yeah.
But it probably won't satisfy all of your needs, right? So think about an immersed boundary type approach, where you can put in any geometry, you can put in boundary conditions with the mesh is Cartesian, and then your geometry gets represented, you know, as a cut cell or mask or whatever it is. I really think, and there's a paper from Anand Kumar's group that does something very similar. So I do think even, and it's not like very complicated, I think even within the next couple of years, we may see something like that, that is somewhat reliable, that can give you an answer that could be, I'm just making up a number here, like 75-80% accurate. In my opinion, that is still useful, because that's not your final thing. That could be your preconditioner, or that's the first guess that you want to explore in many different ways. I really feel that that kind of capability is not fiction. I would not have been as confident in my answer 6 months ago. So right now we're running a summer school, and one of the hackathon groups is actually trying something like that, and I'm actually seeing that in action. So yes, it is possible to get there. But, you know, if you go to a purist and say, hey, look at this answer, they'll only look at where it's wrong. And I think that view is okay from a guardrail perspective. But then the other question you asked, you know, for a class of problems, I think, many tools that even pre-foundation models, many tools we've been developing can actually get us there. And in fact, I even covered one such example earlier when I spoke about if you're able to parameterize that problem, then I think AI can, these ML techniques, purely data-driven, can do, you know, a lot of damage already. And then with these foundation models thrown in, especially foundation models that can interact with agents, right? At least that's my notion of how these things would be useful in the future. Even if these GPT-4-like models or GPT-5 or whatever they are, even if they plateau in their accuracy, their ability to interface with more specialized agents to carry out tasks, in more specific tasks, and then being able to synthesize information back, I think to me that's the most realistic or pragmatic scenario of how these tools will evolve in the next decade or so.
But some would say that this opens up a very interesting commercial or ethical angle, or both. So one is, if you were to make a foundational model, let's say that is for conceptual design, so not super high accuracy, but for conceptual design, most of that data isn't public. You know, like a hypersonic vehicle, not many hypersonic vehicles, all the results are in the public domain, or for or even for like road cars, you know, a lot of those are kept commercially sensitive. How do you think we would get around the data availability issue?
Yeah, that's an interesting question for which I don't think one person can answer. But remember, there are two stages. There is this pre-training stage, And then there is the fine-tuning stage. So when I say these will be useful, the pre-training may not be as sophisticated, but every organization can have its own fine-tunable data sets. And that can be private. That can be as sophisticated as they want, right? And then there may be enough, there is enough open source activity out there, even for something like hypersonics, even though I think, at least in the near future, things will be more closed than open. There is enough open source research happening in this country and in Europe and other countries that I think getting the data sets for pre-training is not unrealistic. But then the magic would be, but that on its own, I do not think is going to be helpful for problems that are not closely related to, the overrepresented parts of the data set. But the fine-tunable parts, I think that will be the most valuable. And as you know, the pre-training is a bulk of the cost, right? It's about 99% of the cost is in pre-training, generally speaking. And then people can have their own fine-tuned things within their organizations.
So how can the community go about and do this then? So what are the practical challenges? You put on the symposium to look at foundational models, but what needs to be done essentially to enable this?
Yeah, I think, anytime a newish field emerges, you need to get people together and talk, right? So that's really the first step that we have organized here. And we had this conference in April of this year. So next summer or early summer, we're planning the next version of this meeting. And it's going to be a really big deal with all the names you hear in the news, hopefully, most of the names at least, to be present. So I think, so that's one activity, right? To be able to discuss ideas, to be able to discuss tools, to have tutorials, to propagate this thing. But beyond that, there are already a few things that are happening in creating these subdomain groups. And at least if some of visions come true, we may have a multi-university government industry consortium. I call it as Future Sci-FM Institute, where we go through this process. But I would like you to look at, there is one organization, I don't know if you know, it's called the Trillion Parameter Consortium. It's kind of led out of Oregon. And they already have probably like 50 universities. Michigan is a part of it, and a few national labs, and not just the US. It's easy website to remember, tpc.dev, tpc.dev. And they're already facilitating precisely the kind of things you're talking about, right? They're organizing, they've talked to ACM, and they've organized access to the journals. They are basically setting up benchmarks. They're setting up evaluations. That is still to support the science, the open science foundation model in particular. But that is the community that is the farthest along in enabling the kind of thing you're talking. But that is not a body that, gives you money to do research, right? But we are, envisioning this kind of institute with, government funding and philanthropy and venture funds to make sure there are also the resources needed. But, starting with some of our activities as part of the next Scientific Foundation Models Conference in May 2025, we'll already have some of those structures built up as, we collaborate with larger organizations. So, if you take CFD, which is our traditional domain, there are those ECOF-TAC data sets, and there are maybe about 10 or 12 such sizable clusters. I mean, that would be a start, but then if you have an open way to bring data in and hopefully some resources to train it, and then more importantly, incentives So I think the incentives have to change. Right now, at least so far, the academic and the scientific community incentivizes certain class of activities as more valuable or more prestigious. And that has to change, right? And I think, to me, one of the most exciting aspect of foundation models is the idea that for the first time in human history, I must say, there is a possibility of, say, thousands of domain scientists collaborating on the same platform, right? Some of them are contributing data, some of them may be fine-tuning, some of them are building the architecture, some of them are doing evaluations, some of them are probing the models, some are developing architectures, but it is the same platform. That's kind of pretty crazy if you think about how it changes the nature of collaborations, which tend to be kind of loose, unless you have a project like ITER and other things. But still, this can be more direct. Everyone's working on the same platform, on the same type of model, and bringing their pieces in. And I think many countries, will start to coalesce around this because of the fact that this is a collaboration tool that is unprecedented. But again, I think the benefit would be when this model kind of interacts with those agents, right? And some people may be developing those specialized agents, like for protein folding or turbulence modeling or whatever. So I think you can unify domains within science and science itself. And this is the first platform that allows people to do that, right? So I think
I like that idea. I think what your vision is more of a, and I haven't heard this articulated in such a clear way. You're saying essentially that we sometimes double down and focus in this fluid domain, CFD domain, on pins or on neural operators, on things, but you're already seeing them as the sort of the agents that a future sort of large language model can be calling, but there needs to be also the investment on the underlying or the main thing that's calling those agents and able to interpret what we're asking. And that's something that perhaps hasn't been as widely spoken about. At least I've not heard this as much, and I'm appreciating you saying this because it's kind of making sense in my head now. And I guess it can learn the agents can learn from what the large language model's doing, and vice versa, I guess, to do that.
I do want to mention one important thing, right? So it is the large model, the agents, and the humans also in the loop doing this general guidance and evaluating. But taken together, I think this has the potential to be a new way of, or to be more conservative here, a new tool to do science, but a collaborative tool that has not existed, right?
Well, you probably know where I'm going to go next with this, because I'm always never sure, and I think it's a global debate on regulation and the ethics. I know that when I've spoken to various, colleagues or people at conferences or wherever, there then starts to be this, light bulb moment where you realize, hold on, you're condensing a lot of knowledge into one thing. And most software packages have ITAR restrictions or have some form that stops them going, to other places. Is it the case? How difficult is it going to be to do this fully open source?
Yeah, well, again, what is open source is the first question, right? Like, whatever is available open source right now as data and use it under the right terms, I think could be fair game for the pre-trained part of the foundation model. And then there's a fine-tuning and the agents that become a little more specific, right? So again, I'm not an expert in this topic, but even in that scenario, there are many things to worry about. What if you spoke about, I don't know which two words you spoke about, but you didn't mention security, right? What if, something comes out of this that could be potentially a risk to national security or, some other thing that we worry about? So that's certainly an open question. And I was comfortable talking about everything before this because I thought about this. I've kind of worked on some aspects, but that's not my expertise. So, but I would say yes. We have to look at this very carefully. But I think what is openly available can be used, right, for that. And then for things that are more, this Open Science Foundation model is not the only science foundation model that would be out there, right?
Yeah.
But the thing there, of course, the risk there is people, organizations, countries that have more access to more resources and more compute and more data will have their own more powerful foundation models. And these are going to be very expensive to train. If you ask me, are they useful? I would say absolutely. Are they always going to be accurate? Absolutely not. But they can still be huge productivity. They can still, result in huge productivity gains. And I think from a national interest, I think countries should be investing in this because of the potential. But is it worth investing $7 trillion, like Sam Altman says? That's a different debate to be had. But I think, I wish in the next year or two, or at least as soon as possible, at least the only thing I feel strongly about this is there is this whole thing about artificial general intelligence, and we will get there in 5 years to 10 years. I think that's a big distraction. Given what these tools can already do and what these tools can do in the next few years without that goal. If that is the goal, I think people will be disappointed, very disappointed, in my opinion. But if you have more pragmatic goals about productivity boosts and scientific assistance, and you're able to work with the realization that these things will never be perfect, they may not be able to tell you something drastically new, but they can still be a massive productivity boost. I think even within the next few years, we'll see great benefits come out of it.
One of the guests in a previous episode gave an opinion, and I was interested to see what you think of this, around the role of academia, the tech sector, and startups. To achieve this vision you're talking about of, a new platform, new technology for scientific discovery, where do you see the roles of all three of them? Where does academia fit into this? Where are startups required? Where are the tech companies needed, or industry?
I'm glad you asked me this, because one of the exciting aspects of the platform that I described earlier was because different kinds of organizations can do different things, right? I do not think, at least in the next 2 or 3 years, academia would be doing the pre-training. Because, you need 10,000 GPUs just to get off the ground, right? So that's not what academia is probably ever going to be good at. But then, almost everything else that I mentioned, right? Data curation. Traditionally, academia has been keepers of knowledge, right? And this is just baked in, right? Maybe they don't have access to all kinds of data, but the open data, right? So that is where academia is at its strongest. And then let's go downstream, right? Let's talk about developing specialized agents. What does academia do? Basic research, specialized narrow. So there is the clean role there. And maybe even in the fine-tuning process. And then, if you talk to people who are developing these science foundation models, and probably any kind of foundation model, right now, they're not complaining about, when I talk to them, they're not complaining about data, they're not complaining about compute. They're saying the most important thing is evaluation and feedback. I can, again, envision a future where, as part of many classes that master's or PhD students or undergraduate students take, where they may be evaluating or fine-tuning or creating data, right? And this kind of expertise and human scale only exists for these kind of tasks, only exists in academia. And of course, there's a lot of basic research needed to improve architectures, to, as people say, coming up with much better ways than just complete the next word. This iterative process. So this is where academia is at its strongest. So except that one pre-training block, I think academia is in a nice position to contribute everywhere else. And then you have national laboratories who are very well placed for certain parts of this ecosystem. How do companies come in? That complicates things a little bit because mostly these are for profit. And so they have their own goals, and some of those goals, thankfully, I think overlap with some of these broader ambitions we have. And certain companies, it is in their best interest to sell more GPUs. So I'm sure they can help in addressing part of the research and the computing resource kind of spectrum. So I think all these organizations can have a very clear role in this entire platform. And that is, again, very exciting to me, right? Even companies that have different goals than academia, and national labs, which have slightly different goals than academia and companies, I think there is still so much common ground that maps to like one part of the platform or the other.
I don't know if you have this similar thought, but I do often wonder, I mean, I don't envy the people at the top of Siemens or Dassault or Ansys or Cadence who are probably faced with a complication. Do I bet the house essentially on, really going in on AI and machine learning and this idea of scientific foundational models, because, a lot of scientific discovery is done using their billions of dollars worth of software packages, throughout engineering and science? Or do we continue and make even better these high fidelity, physics-based simulators? Do to me, there was not, well, I guess there is in large language models, there were companies already doing things, and I guess Adobe and Microsoft and others are in there. But do you see my point? What role do you see for these massive companies already in the simulation space who arguably have the most to gain or lose from these new methods?
I'm glad you just restricted your domain to simulation companies.
Yeah.
So that's easier to answer. If they bet the house on foundation models, I think it would be foolish. I think if they bet the house purely on AI, that would also be foolish. But if they ignore this, that's even more foolish. So that is, I think, a happy medium where whatever you've been doing and whatever you are very good at, those can be agents. Remember, agents don't just have to be AI agents, right? An agent could be your beautiful solver, right?
Yeah.
And it maybe there is an AI angle to it, but it doesn't matter. But I think, I mentioned earlier about probing and evaluation. If there is something that's fairly trustworthy, like your solver that you've developed for 20 years, that can play an enormously useful role in this evaluation processing. The foundation model can generate a prior that can be evaluated or fine-tuned, right, and brought back in. So whatever you have been good. I don't think AI fundamentally changes many things that we have been doing. In fact, I think it can help drive more value. Also because AI on its own has many shortcomings that cannot be addressed using data and AI alone. So yes, I mean, for those simulation companies, being cognizant of some of the developments, and then even taking open source models, and maybe you don't want to spend enormous amount of compute on this pre-training stage, but collaborating with institutions like I mentioned earlier, right? If we have an open science foundation model, then maybe Siemens can provide, you shouldn't name particular names, but particular companies can provide services in the context of the tools that they already provide, right? So I think there are a lot of opportunities there at the intersection of what you're already good at with all of these things happening. And of course, some other companies that I think certain simulation companies that are already part of a bigger conglomerate, I am absolutely sure every company has this in their vision, and they may have their own context-specific models that will be interfaced. So the short answer to the question is, don't bet the house fully on this, but it's not something that can be ignored either. But at the same time, I'm sure there is completely unrealistic expectations all over the place from customers and upper management.
Yeah, it's kind of interesting. If I speak to some of my friends who work in industry, and it's hard to know because sometimes you don't know whether you're in the bubble, by being in a certain thing, but they are almost to the point where they're sick of people pitching stuff to them. And, it's almost, the classic response is, well, we've had reduced order models for decades, you're just rebranding this. So there is, I think, the danger of some of the hype of AI in general. And if you go in too early into a field promising the world, it can sometimes burn trust. Or do you see that sometimes in your discussions?
Yeah, for sure. And I don't know if you know, I have a startup as well, and it's called Geminus.AI. We've been going for about 5 years. And even before the foundation models, we've had this same kind of challenges, right? People think with like very little data, you can create magic. But I think what has worked for us right from the beginning is by setting these expectations and saying, hey, this can, just be very clear about what it can do well and what it could do and what it cannot do. And being very clear and, being honest about it, I think there is a way here. But you're right. We have faced some customer scenarios where understanding of capabilities of this technology is so unrealistic. But it's an iterative process. Ultimately, if you're able to show that there is something that can be done at lower cost or, in quicker time with reasonable accuracy, then that iterative process, I think will take hold. Ultimately, right, nobody's going to argue against actual utility, right? It's the perceived utility and hype that cloud things up.
One of the things I've tried to in all the episodes where possible is a bit of career advice, I guess, and you've rose to be a very prominent and successful professor at a leading university. You have your own startup. Many people look at people like you and they often wonder, well, how did you get there? How can I get there? This is a difficult question to ask because I know it's very dependent on people's roots and everything. But what have you learned along the way? If people are wanting to go into academia, they're wanting to rise, would you do the same as you did? Are there paths that you would take differently as advice you would give? Let me frame it. You're a PhD student now. Yeah. You're already doing a PhD, let's say in fluid dynamics, and you would like to become a full professor one day. What would be your advice to that PhD student?
Okay, so that's a easier question to answer than the more broader question, although I have been asked that question quite a few times, right? So I think I'll address the first part very briefly and then get to the second part, right? For me, the only thing that has driven me is curiosity and, not defining a control volume saying this is what I'm interested in. But being intensely curious and then slowly growing the control volume to account for certain things. And if you say I'm successful, then in your view, I'm successful, but I don't define things that way. But what has worked for me is just pursuing the curiosity, but also not forgetting what needs to get done on the side, right? To keep the trains running on time. But yes, what advice would I give my PhD students? Maybe I'll interject another question I get asked a lot, right? When people ask about, I get asked this, I've given about 20 talks over the past few months just on these AI topics, and this question comes up. I want to specialize in AI for science, or my group wants. So where should we start? And what should we be focusing on? My first answer always is get really good at the science. Because the AI is not going to solve any scientific problem to a greater degree than what the expert solves. But if you have a very good understanding of the domain and you do not lose any rigor there, and then you pick up the essentials of AI, then it can help you be much more productive and hopefully leverage it in the right way. So I think I would give the same kind of advice. The foundations are the most important pieces. Without losing rigor in mathematics, physics, chemistry, and biology, where it matters, then every AI and all of these techniques that come about, right, are basically layers that are built by combining these different nodes. And I think for those who have that perspective and have a solid foundation, I think moving into new areas is much easier. But I think your question certainly has one important aspect that I want to highlight, right? So if you think about how academia has changed, or even nature of research has changed in the past 2 decades. Say when I was a graduate student, everybody pretty much in my line of work would write a solver from scratch, right? So that has changed completely. One PhD would be running an LES properly. That was, I think, at Stanford, Parviz Moin would say that even 10 years ago. So all of that is changing. So, and to be a faculty member, to be a professor at a university like Michigan, you were the expert in your domain and you had a big impact in the field. That has changed, AI or not, right? Because globally there is just a lot of researchers, looking at these topics. So if your foundations are very strong, and this is not just for academia, this is for industry and financial labs as well. If your foundations are very strong and then you're curious, then without losing that core aspects, being able to navigate into newer and newer areas and adapt and be flexible, I think that becomes easier. Mm-hmm. And my PhD students, I call the PhD program, at least in my lab, as a training exercise to equip you with the skills rather than just to solve a problem from end to end. So gain as many skills as possible, but the most important thing is the rigor that makes you see things and connections and makes you navigate those as seamlessly as possible.
Very rarely meet academics at the top of their profession who aren't genuinely excited and interested and feel almost like they're running their own startup. I know you also have a startup, but you kind of compared to in industry, I speak to far more people who are a little bit miserable and sort of depressed. And I know academia has many problems, but normally when I speak to an academic, they are still genuinely reasonably positive about at least the flexibility they have and the ability to set sort of their directions.
Yeah, it is like I never left grad school, or sometimes I've never left kindergarten, right? I get to play with these amazing toys and tools, and get to collaborate with people. It's just an amazing place to be. But it's not without its challenges, right? Especially the first 7 or 8 years in academia can be extremely stressful for some people, not everybody.
Yeah.
And of course, the move from postdoc to assistant professor is also very competitive. And it's maybe not for everybody, but I think for, like you said, if you're genuinely driven by curiosity and passion, and you are, you're paying your dues for things that you have to pay your dues, I think it's an incredibly rewarding career.
So maybe as a final question, as a bit of an outlook to the future, and I know these are always hard, so maybe more thematically where you see it. If you were to fast forward now and you're doing your symposium in 5 years' time, what do you think will have been the big achievements by then? What do you think will there still be the Gen AI hype and it'll keep going? Will there be the winter of AI and people will be moving on to new things like quantum? Or where do you see in 5 years' time the academic world around, let's restrict it to fluid dynamics, just to make it a little bit easier to predict? Yeah,
first of all, even next year it won't be my symposium. It will be the community symposium. I think a whole bunch of us together will come together to organize it. Yeah, but I especially in AI, right? Predictions never go to plan. I think in 1970, one of the most famous AI researchers ever, Marvin Minsky of MIT, who started their AI lab, he said in 3 to 8 years, we'll have a machine with general intelligence of an average human being. And I think in 1965, they said within 6 years, we will have a computer that will beat the best human chess player. So in that sense, I would say, I think these things will happen at some point, but what I have learned from listening to many thought leaders, including Jeff Hinton and all of these people, thought leaders tend to compress time frames a lot, right? So I will not give you precise answers on what will happen in 5 years, but I feel there may be one big leap in the capabilities of models like GPT-4, but I don't know if it will be as big as going from 0 to GPT 3.5, but there'll be one big leap there. But in more restricted domains like turbulence modeling, I think, again, maybe this is more of a hope. There is no two camps. There is only one camp. And because you said turbulence modeling, there should only be turbulence modelers who use these tools better. There is no AI people and traditional modelers. So I think it's already been slowly coming together because, I'll be honest, right? In 2012, I could write anything and it could be published in this topic because it was just new. And then slowly, people had to show that I'm not just doing a priori learning, I'm being model consistent. And then almost every paper that people are working on now, it has to show some level of generalization, right? Which I was not doing in 2013. I was training and testing on same or very similar things. So in that sense, the field is moving. But I still have not, and because of the nature of how funding works, if you get $500,000 from NSF, you're addressing a very specific question, and you'll publish papers to address that very specific question. We need a broader thing. Like in the US, we have things called MURIs, multi-university research initiatives. So that's like order of $7-8 million. So there now you're getting different kinds of people together and not just developing methods. You want to develop some solutions, and that still has not happened. Again, maybe that's an excuse. My group has had enough different projects that maybe we could have done something like that. But to have more unified projects and collaborations where the goal is to actually create better models rather than showing what your particular contribution is doing. So I think that will happen, because even in terms of publishing and even in terms of funding, so far, you being able to show a few things has been good enough because the field didn't quite exist or mature. But as with any field, once some of the lower hanging fruit have been picked, then the demand, the market would desire actual progress. And I'm pretty sure in 5 years, at least it's very clear what the market desires, and I think it will drive it towards better models. I still don't think, data-driven or not, generalizable turbulence model exists because of many things I go in that paper that you referenced earlier. But I think for particular domains and flow regimes, it just needs. I think the methods are there. The community is big enough. People just need to come together under the same umbrella, and then some people have to come together, and I think you'll already see a lot of benefit.
Well, I won't test you in 5 years' time on that, but I'm pretty sure you're right that it seems to be one of those ones where there's enough swell of people working on it that it seems irreversible now in terms of momentum. It doesn't seem like quantum, where there was this bit of a buzz, but then I know that's a whole other topic, how machine learning is sort of, push quantum aside a little bit from a lot of people's minds. But it feels like with machine learning and AI, there's almost every person you speak to in the community is doing it in some form. So it feels like it can't really turn back. But yeah, whether there'll be I guess in the weather domain, things like ForecastNet and GraphCast have had their big moments. I guess what you're referring to is maybe there needs to, if there is one in the CFD, for example, domain, that would be enough of a catalyst to then convince industry as well, where it seems maybe there hasn't been that GraphCast, ForecastNet sort of moment yet, I would argue, in CFD. To push it.
I would say that it's not that the moment hasn't existed. The question has not come up. The weather prediction is a sweet spot, right, for these techniques. Lots of data, lots of good quality data. And then the question you're asking is, you take one system and you're saying, predict few days or 2 weeks. That's the only question you're asking. And I think for that question, I would say the tools are fairly good. And I say fairly good because, in my opinion, these models don't need to be as sophisticated and as expensive, and they can still do a nice job, right? But you're right. So to me, that's more like the sweet spot problem existed, and the question was narrow enough that you could, and those are the problems where I think AI has been really doing well, right? Like AlphaFold is the prime example. Very specific, very narrow question. Now, if you say, can we go from 2 weeks to climate, then all of the work that's been doing then needs a lot more work. To me, the turbulence problem is more like the climate problem rather than the weather problem.
Yeah, which is why I guess I was originally asking, like, the maybe we need to set our standards a bit lower, or our sights a bit sort of narrower on, like, even if you could develop something that proved you could design a commercial aircraft, that is the thing where I guess the pitch has often been by some, like, all of CFD, which just seems almost like that's like predicting the weather on any planet in anywhere in the universe.
It's forced by definition, right? But yes, I think every organization within their confines, I think even full aircraft design is a bit too big for now.
Yeah, that's true.
Yeah, it can change. But even if your thing is not, the weather prediction problem, it's end-to-end AI, right? So that's like really clean. I don't think end-to-end AI for something like aircraft design, I don't think that'll ever happen. But in this end-to-end spectrum, I think already like a few gaps can be like closed. And because there are human experts in the loop, this can be beneficial. But otherwise, these tools are not useful without that human expert being in the loop and guiding them.
Yeah.
But I think as time progresses, I think more of these gaps can be addressed, and more productivity benefits can be achieved with not much more sophisticated tools. It's just having the expertise to like integrate them and guide them and do due diligence.
Well, I feel we could probably talk for hours on this, which is the danger of AI and sort of science. It sort of becomes one of these, drinks over a beer in a pub.
For sure, yeah. Always a pleasure to talk about this, especially with you.
Yeah, thank you so much. And really appreciate it. And I definitely would recommend people to follow you very closely. I genuinely, everything you've done, you seem to have a very good way of, whether you know it or not, sort of predicting the future or predicting the path of science. So, because I didn't know anything about the foundational thing, and as soon as I saw you put it out, I was like, see, he's done it again. He's definitely sees where it needs to go. So
It's just a combination of having some curiosity and then having the right people around me.
Well, so, okay, yeah, very modest, but
very fortunate to have a great group of people with me.
Well, thank you again, and hopefully we get a chance to see each other at some conference in the future. But for now, thank you very much.
Yeah, see you around, Neil. Thank you very much for this.